Something, yeah. I'll state the theorem almost immediately. Great. Thanks for the invitation to speak here. It's great to speak at this conference. The organizers actually asked me to both talk about this specific paper and to simultaneously give some kind of overview or introduction to how Galois representations are thought about in the Langhans program or something like this, I think. So that was the brief. I will doubtless fail, but I'll do my best. So this is joint work with George Boxer and Frank. And it's a very short paper, and it's on the archive. In fact, I was looking, the proof of the theorem is shorter than the introduction, and the whole paper is only 11 pages. So you can read the whole thing if you want during this talk. I'm going to start by just trying to state the theorem, which will have some undefined kind of terminology, which I'll sort of maybe try and fill in slightly as we go. But the theorem is that there exists an integer n bigger than 1 such that there exists a Cuspidal automorphic representation weight 0 and level 1 of something, or GLN has also a representation of GLN. Right, sorry. Great. Yeah, I stated it wrongly in my notes, brilliantly. Okay, and we put n bigger than 1 because when n equals 1, there's obviously an example of such thing because it turns out the trivial one-dimensional representation. Example. This trivial such thing exists for n equals 1. And our construction, I think I'll give you a construction in dimension, I think it's 106. The smallest value of n that we prove this for is n equals 79. I might explain something about that at the end. Almost certainly these things exist for all sufficiently large n, and sufficiently large probably means about somewhere in the low 30s, but we can't prove that. So I will try and give some motivation for this a bit later. It's kind of hard to kind of give the motivation that maybe we cared about without representing out the proof. But a kind of non-example is what happens if n equals 2. If there were such a thing, it would be a modular form of weight 2 and level 1. So the problem is the Cuspidal modular form, so we place a form like S2. Level 1 means full level SL2Z, and this space is 0. So that's kind of a non-example. So the smallest kind of weight for a modular form of level 1, full level SL2Z, is 12, where you have Ramanujan's delta function. So I'll come back to it. And an earlier result, I think what was known about this before, there's a result of both Ramanujan and Miller, exactly, it's proved in the two papers, but they proved these things don't exist for n between 2 and maybe less throughput. So there had been some speculation that maybe these things just don't exist at all for any values of n. And unfortunately, it's kind of rather hard to do computations in dimension much bigger than 26. And in particular, no one knows how to do computations in the sort of dimensions where we now expect them to exist. Yes. That's gonna be coming up. I'm just sort of saying this is known, this is, and Next, I will try and say something about what weight zero means. So I'm not going to explain what a Cuspidal representation is, but it's some generalization of modular forms. So level one means, well, let's say, so pi, to my notation following you very much for Cuspidal automorphic notation. Where you rather like GLN and Q, I write more properly to go hang on to the L's. So level one just means that this has invariance under, I guess, so the pi L has invariance under the GLN ZL. But unramified, like pi L, unramified. Now, and then what's the rather confusing weight zero? Without confusing our weight two modular forms. The weight zero by definition means that pi is cohomological to the trivialist. Okay, so and that means in fact the kind of theorem, probably this is the title of the talk, is equivalent to asking for the existence of some Cuspidal cohomology. So just to say that. So this is, again, I'm not going to find this, but I guess in Brandon's talk yesterday, there was some mention of the Shimura isomorphism for GL2, where you can see that you can compute the sort of cohomology of GL2Z in terms of modular forms of this level, of level one. And the cuspidal part is the part that's quite cuspidal, bit of a secular. So in general, this cohomology without this can be computed by means of automorphic forms or notations. And we're asking that you actually see this in cuspidal. So n equals 2, you don't.
This must be a constraint on pi infinity.
Exactly. Yeah, yeah. So this is being cohomological. This is equivalent to saying for pi. By definition, that's pi infinity.
When n is greater than 2, what is pi infinity?
No, I mean, it's a representation of GLN. I mean, it's a GK module or something. It's a representation of GLNR. You can ask if it's got cohomology. I'm not sure what helpful answer you want. I don't know what flavor of answer you want.
There's no longer a discrete series. It's 2. No, but there's always right. Maximal. There's always a maximal value of the series.
I'm not going to repeat everything that's saying out loud. Just to be clear.
Is there only one of them? I guess. Is there only one class?
I think maybe 2.
Sign.
There's a sign that can come up. But yes, essentially, this is telling you what pi infinity is, and you're asking that it's contributing to cohomology, and it's got trivial coefficients. So why do we call this weight zero? It's because you could make the same definition with kind of any algebraic representation of GLN, and this is the one corresponding to weight zero representation of the algebraic group.
Are these supposed to be algebraic in the sense that there are Galois?
Luckily, yes, for the theme of my talk, so that I can nicely segue onto the answer to the other question, which is, are there Galois representations? And the answer is yes. So for any such pi, one expects, I'm actually off the top of my head, I'm not sure that is the theorem or not, but one expects to associate Galois representations follows. Well, we're going to list the properties we expect, and we definitely don't know all these properties. So for any prime P, so if it's P of prime, then there's going to be a representation that I'm going to call rho pi P from GQ will be the notation for the absolute Galois group cubed. It could be an n-dimensional representation. It's continuous. And the following properties. So any set I mean ones which are of level 1 and weight 0. So the level 1 condition, well, first of all, for all the primes L not equal to P, it's just going to be the Galois representations done around. So the shifted to P condition group L is unramified, L is not P. At P, you don't get something unramified, but you get something crystalline. And this weight 0 condition is also encoded here. The hot take weights are 0, 1, 2, 3, 10 minus 1. Take weights. One. And also the cuspidalities. You should have these things even if we drop cuspidality. Cuspidality should be corresponding to these representations being experienced. And so far I've not really connected pi and rho pi P, but the connection is that I'm not going to go on about this too much, but given you are unramified, you can then consider the characteristic polynomials of the Frobenius L and the conjugacy class, if you like, of rho pi P of L is going to match with the eigenvalues for the Hecker action on this. That's the Hecker operator exactly on. You can vary it in pi L. From that, you can extract the conjugacy class and it's going to match in GLN, and it's going to match for all. L1 equals P, and there's actually a similar recipe at L equals P. This is some characterization. So
when L is infinity, I have a guess for what this is.
So for L equals infinity, there's also, yes, the complex conjugation should be odd. So it should have this, you're getting an element of 2, and you're going to get it's as close to many ones as well.
Nice, that's my guess.
Exactly. Right, and conjecturing, which I'll do in a moment, if you could construct for a single prime P a Galois representation of these properties, you get a pi. That's part of what's known as the quantum laser language. And in fact, the way we're going to prove the theorem is by, in some sense, by constructing the Galois representation first. Although in some sense, that's slightly misleading, because in some sense, we kind of simultaneously constructed and see the idea behind our construction is to construct a Galois representation. So the irreducibility, I should say, is key here. It's very easy to write down a Galois representation with all the other properties apart from being irreducible. So kind of like the non-example is if I write epsilon for the p-adic sigmoid character, Q, then I could take sort of rho to be the direct sum from 0 to n minus 1 of sigmoid characters minus I. So my convention is going to be that sigmoid character has positive rate minus 1. So this is a representation which is ramified outside P. It's crystalline at P, the whole code is 0 up to n minus 1. But it doesn't correspond, it's not irreducible, it doesn't correspond to some Cuspidal convention. It works according to something sort of some Eisenstein series types. Some of them.
So it will be like
yes, so yeah. Oh, up to some issue of what the conventions are, but possibly literally corresponding to the trivial or to other constituents of the corresponding parabolic function. Right, that was kind of the introduction. Are there any questions? I'm going to shortly review something like this more concretely, but not before it's going to come to construction. But maybe I'll first of all just say kind of, I said word spontaneous alignments, but maybe I would kind of write some version on the board. I'm not sure that there's a precise exact conjecture that has this name, but some part of a conjecture with this kind of name would be the kind of existence of bijections to be uniquely specified between, if I can actually also state a correct conjecture, algebraic Cuspidal automorphic representations of GLN Q, or if GLN delts, in the same thing, by definition. Irreducible rank and geomotives, whatever one's going to make that. And then some things more like Galois representations. So here, some fixed prime P, so it's irreducible representation rho Q, GLN P bar, which is continuous, unramified, almost all L, so all but finite many times L, and the wrong P. So this bijection, conjectural bijection here, if you then specialize the kind of case of weight 0 and level 1 up here, you find that that's corresponding to the conditions I had over there, being unramified outside P, and the Durama P getting strengthened to crystalline and specific state weights. So this should also be in bijection with what are called compatible systems. Of representations. This. So you have one now for kind of index these rows of P, so you have a representation for each prime P. And the compatibility between them is supposed to be expressed by the characteristic polynomial genius at unramified places, and then ask the P variant That's what a kind of compatible system of representation should be. And in general, of course, we don't know anything like this, even if you were to adopt the perspective that we sometimes do of sort of collapsing these two things to be the same thing. You think of maybe compatible systems of Galois representations being some incarnation of motives. And the idea being that you go from here to here by taking the cohomology. But it's not at all clear. Of course, maybe the one arrow that's easy is this arrow, because this is the arrow of just taking representations for every prime p and just fixing one prime p. So that's getable. But going back the other way is hard. If you have the representation of single prime p, it's typically not at all clear how you get the other ones. In particular, I should say, because these are continuous for the p-adic topologies, it's definitely not the case. These representations, in general, like arise from a representation to Q bar or anything like this. It's not the case that there's just choose an isomorphism from QP bar to QL bar. That's not something you want to do. And going from here to here is associated Galois representations. That's something we know how to do in some cases. I'll talk about that, but certainly not in full generality by any means. And going back this way is the problem of proving the modularity or automorphy of Galois representations. It's the kind of thing that goes back closely to the kind of like sort of modern technique we have, is the stuff going back to the work of Andrew Wiles on so proving modularity of, in that case, the modularity of elliptic curves, but by thinking of the associated Galois representations, which are the paper ones. Okay. So yeah, great question. What does the crystalline condition correspond to? Literally, if you're unramified at the prime p, that's the same as being crystalline at p rather than just a graph, conjecturally. And for the primes, if I'm looking at p-adic representation, being unramified at L is equivalent to the force of representation being unramified at L. So more generally, there's this thing called the local Langlands correspondence, and that actually tells you basically how to read off what the local factors of orthogonal representation are from the local Galois representation. So in some sense, if you're given a Galois representation, you could try and sort of literally write down what you think the orthogonal representation is, but you can't prove that it's actually a representation. You can write down some local factors, but you can't see that they give something local. So yeah, so I'm not going to write too much, but a very special case is if you take this to be elliptic curves over Q, then the things over here correspond to certain eigenforms, modular forms of weight 2, with coefficients being rational numbers, being the Fourier coefficients actually being Q rather than Q. And there's some bijection, and the bijection preserves the conductor. The level of the modular form corresponds to the conductor of the elliptic curve. And that's kind of an instance of the kind of thing I was talking about here. So in particular, the primes dividing the conductors of the elliptic curve are exactly the ones where the Galois representations are ramified by their own bulk separated. And the same about being crystalline is the kind of it's a version of that for abelian varieties by Beta and Coleman, maybe. Sorry, blanking. Okay, so maybe I can just mention the kind of sort of n equals 2, and you take I'm using delta function with the corrected against 4, which is equal to 2 pi I z. Z. This is a modular form, an eigenform of weight. Well, this is now, excuse me, this is weights in the usual kind of 19th century sense of weight of modular forms, level 1. And so you get from it, yeah, the representations at coefficients here are integers, and so you get representations of G of P. And these are crystalline at P and quadratic weights are 0 and 11. This is not an example of the category. It satisfies these are irreducible, but they want to be 0 and 1 and they're 0. Here's not an example for these Galois functions. Any questions? Okay. So sometimes it's easier to do things on one side of this correspondence or one of these corners of this correspondence than others. So I guess an example is the proof of Fermat's theorem, if you like. So in kind of growth outline, what happens is you take a solution to Fermat's theorem, putative solutions, you make this Frey curve, this elliptic curve that looks kind of too good to be true. And then the way that it was proved to be too good to be true by Ribbon following Serre is to show that the associated Galois representations can't exist. And the way that ultimately works is you look at the Galois representations, you study their properties, you think about congruence and so on, and you eventually, by moving around, you get another kind of Galois representation that would have to correspond to a modular form of weight 2 and maybe level 2. You get to a space of modular forms that you just know doesn't exist. Sometimes, on the other hand, it's easier to prove that the Galois representations exist or don't exist. For example, the kind of results that sort of in a similar flavor to this, but in the opposite direction, it's because the Galois certain properties. Fontaine was able to prove that there are no abelian varieties with over Q with everywhere given reduction. There are no abelian varieties over Z by proving that the corresponding tape modules couldn't exist. By sort of thinking very carefully about the ramification on the Finite flat groups. So our kind of approach to this question is to sort of maybe slightly go back and forth between the kind of automorphic side and the Galois side, which is something that happens a lot in the Langlands program. And we first of all kind of come up with a recipe that I'll explain for trying to construct a Galois representation like this. And we then use some theory about modular forms to make some Galois representations that we can feed into this recipe. Okay, so that's probably even vaguer findings for all of you than it sounded to me. Let me try and say something much more concrete. Which is that the way we kind of use, the way we can kind of build Galois representations is by thinking about congruences, which is kind of encoded more formally in Mazur's theory of Galois estimations. This is from time ago. So I guess I was giving you examples where I was sort of talking about how one could prove something by maybe showing that there was no object of some kind in one form of this, introducing there was no object in the other. What's true more generally is that, or should be true if this picture is correct, is that you can often get finiteness statements, conjectural finiteness statements for Galois representations for motives by thinking about automorphic forms. So kind of a sort of basic observation is that spaces with automorphic forms, automorphic modular forms, or fixed weight level are finite dimensional. You only have finitely many modular forms of any fixed weight and fixed level. And so if you believe in this picture, so then naturally you're forced to believe that the corresponding statements should be true. Again, just because if you believe the projections are there, that's automatic. And again, I think Brandon talked yesterday, if you start reducing things mod p, which you can do, so on the side of modular forms, by reducing things mod p, I mean I have, for example, these kind of Q expansion, I can just reduce all the numbers mod p. On the side of Galois representations, I'll write this on the board in a bit, but these representations always land inside some lattice because the Galois group is compact, and so then you can reduce that mod p. You can get mod p Galois representations. But if you fix the level and keep increasing the weight on the automorphic form side, you can see that eventually you don't get anything new. There's a phenomenon that, for example, all modular forms, if you look at the mod p, are congruent to modular forms of weight at most, something like t squared minus 1. So that leads you to conjecture that for any finite set of primes S, there are only finitely many isomorphism classes of semi-simple, you like it's irreducible completion very far, now Q, the QL and FQ bar, which are unramified outside S. Maybe I should say S union V. So this conjecture doesn't literally follow from this conjecture as stated, but it morally does, and it's very close to it. So, as far as I know, no one has any idea how to prove this, but this should certainly be true. And I think a takeaway from this is that it might well be hard, in some sense, to start constructing mod p representations like this. This is probably not an easy problem because there's only finite many of them. They're going to be some possibly quite sparse sets. You're certainly not going to find them by writing down a moduli space. So, in terms of this question over here, we're certainly going to want to get a Galois representation that's unramified outside of P, so S to the empty set. And so maybe what we're going to have to face at some point is just finding the reduction mod P of this representation. That's going to be something that we're probably going to be kind of forced to do some trickery to come up with. And then Mason's idea was that while these objects are somewhat atomic and maybe a little bit random or something, you then think about fixing such representation and considering all the different ways you could lift it to a p-adic representation. There's a lot of structure there.
Okay, why do you not have to bound this exponents?
One explanation. So the question is why, when I make this conjecture, would I not have to bound the exponents of the conductors here? And I'm trying to think of a good answer. I mean, I think simply, I'll come to this in a minute, but you kind of, for sort of various, at least moral reasons, you might hope that such things could arise as the reductions of automorphic representations of the same level. And then if I'm looking for things unramified, sorry, I'm saying that in a backwards way. It's a better answer. I mean, a better answer, I think, is just thinking about the moduli space of mod L representations of the Galois QP. I'm thinking, I mean, I think your question is related to are there many
Could it be that given a real R, there's always a lift where the conductors have to put into less bounded way that you might expect, like in Sarah's convention.
Right. And another question is, am I actually stating a correct conjecture?
You want to take like FQ rather than FQ?
Yeah, I think maybe I'm just stating a dubious conjecture. Maybe that's the.
I think you can make the field the finite field.
Yeah. I think I'm just combining too many conjectures. So that's given. Thank you. Let me just like. Let me state what I actually. Yeah. So I think the answer is I'm just talking nonsense. So let me state a conjecture that is correct for what we want. Since I don't really care about what other, so like unramified outside. Yeah, I think what I was saying was most probably false. But part of the problem was that we had the S was empty in my head, and so now I've made it empty, and now we're back on save that. Okay, so this is a conjecture that I do believe. Of course, I believe anything I'm writing forward, so I didn't take too much weight in that. So these are going to be some objects that are just some kind of finite set that we can't do so much with. Yes. Then that's much more reasonable, yes.
It's also trivial,
but it's true for kind of stupid reasons in that I'm now bound to the degree of the extension and the ramification of the fixed field of the kernel. So yeah, sorry, too strong a conjecture there. Maybe someone can disprove what I've written down before. Maybe for GL1, yes. Yeah, exactly. Sorry. Shouldn't deviate from my notes where the set was empty. Very dubious. Okay, so what did Maser do? So Maser kind of says, like, let's fix, and maybe I'm going to try and just keep unramified outside P. So fix a representation, and I'm going to make it irreducible simplicity. And maybe I'll even just actually have coefficients in FP, again for simplicity. If you have a continuous representation like this, it is valued in some finite extension, again by arguments. In fact, all I'm going to care about is the case of FP, and let's fit this to be irreducible. And then you can consider the moduli space of liftings, maybe a formal moduli space of rho bar. Sorry, liftings of rho bar to a representation for rho and GQ. Let's just consider maybe things to rings like GLN R, where R is perhaps complete local material with residue field. So by lifting literal rho means the definition is a map here, and then the composite here is supposed to be rho bar. The moduli problem is, and he showed that there's Okay, and I should also consider demand that rho is also unramified outside P. Fix that demand. So an example of such an R would be like CP, for example. And then those would be kind of lifts that satisfy the events of efficient fields, probably give up. And so what Nathan showed is that there exists a universal up to conjugacy, which I'm going to ignore. So there's a formal moduli space. For normal spectrum of the sum of universal. And this thing, I'm demanding an unramified outside P, but I didn't yet say that I was going to be de Rham or crystalline some fixed Hodge take weights or anything like that. And so this thing has some chance to be interesting, not just have find many points. And you should certainly think that this is a just a power series ring in some number of variables. Not literally going to be that, but it will often be that like that. So this is the kind of thing where this actually has some geometry, in which it's only a sort of formal completion. But there are sort of lots of points, and you can now imagine trying to actually do something because you aren't just looking for sort of one individual mod P representation in some finite and slightly obscure set, but now you're actually maybe looking at some quite big geometric space that you could try and do something with. Okay, and then inside this, there also exists, for example, closed subspace. But R with 0 -1, where the restriction that's equal to P is crystalline the Hodge take rate. It could be empty. But there is at least a close conditions. And there's nothing special about these Hodge take rates. Crystalline like the turn to the Rham of some fixed, something goes down with conductor and some Hodge take rate, something like that. But okay, so I've translated this into some more formal language and some other problems. But then the slightly amazing thing is that there's often a local to global principle for this kind of case. So what we want to do, find a Galois station, we want to show that this has some points. This actually has lifts, characteristic 0. So we kind of want this moduli space. Points. And so an obvious necessary condition is that, well, instead of thinking about my global Galois representation of Galois group of Qs, the condition of being crystalline with these Hodge take weights is just a condition at the prime P. So I could consider the same kind of setup where I restrict everything to a decomposition group of P. And then I could say, well, if I'm producing a global Galois representation, with restriction to the Galois district QP is crystalline with these Hodge take weights, but it better be just possible altogether to find a local representation. In other words, if I restrict, now I'm not useful. I'm going to erase this proportion. The kind of necessary condition is that restriction of rho bar, this is our representation of deeply distributed free GLM FP must admit lift to crystal representation GQB. So GLM CP bar, but might just be CP, but some given to extend scalar slightly with Hodge shape rates. Zero. There's just some trivial local condition that has to be satisfied for the existence of the global representation with the local properties. The local property had better not be backwards. And it's certainly not the case that such a thing should always exist. So, for example, if n equals 1, then the crystalline representations are just unramified characters times powers of the 6th atomic character. So to ask that I had something here with a lift with Hodge rate 0 is the same as asking that the rho bar, which is our character, is unramified at P. Certainly, if P is bigger than 2, then the more P6 atomic character, for example, something which is not, which is ramified. So we've not satisfied this. This is certainly a constraint on kind of local Galois representation. Okay, but the amazing thing is that sometimes either kind of rarely or frequently, depending on your optimism or pessimism, there exists kind of a local global principle saying that if the local this, but if there's no local obstruction, then so is the global. So, for example, when n equals 1, you can easily check to satisfy you have your representation in multi-representation everywhere ramified. It certainly has an everywhere ramified lift, which is what the problem comes down to for n equals 1. So this is not, I wouldn't want to try and state a precise and general theorem about this. I just tell you how you can at least try and guess when this should be true. So, so one can compute an expected dimension, full dimension of this ring, you name like this there, of R minus 1, just by doing calculations in Galois cohomology. Again, there's nothing special to the fact that I'm the condition with my representations are ramified out everywhere outside. I can use every number field. I can go to another group, group or something. You can always make some calculations, and basically by kind of just thinking about generators and relations for Galois groups, you can kind of make sort of a presentation. Use it by sort of there's like a Galois H1 number of generators, and then a sort of H2 number of relations, which may or may not be trivial. And so you can guess some kind of make some kind of guess as to the dimension of this detonation ring. And usually, in some sense, if you just choose like a random number field or something, or you can just do this calculation naively for n bigger than 2, the expected dimension is going to be 0 or possibly even negative. And that would be kind of bad, because that would suggest that you're not very likely to find QP bar points of a ring which you kind of expect to be the 0 ring, or maybe just the ring FP. On the other hand, sometimes the expected dimension comes out to be 1, and in which case you could kind of hope that this ring is actually something like ZP. And for example, get 1 out of this calculation in the specific example I'm thinking about. If this rho bar, this global representation, is right, essentially self-pure. So for example, it's maybe preserving some symplectic form. Then if you consider this the kind of subspace of lifts, which are also some self-duality, then you get that this expected dimension is at least 1. And that's at least telling you it's not completely hopeless that some local global principle could hold. And then there's kind of a rabbit out of the hat, but it's sort of an old rabbit. There's a theory of potential automorphic. I don't know many people since, and that's part of the part of revealing that is this wild method, and also an argument beautiful dimension version. And often improved that this ring blah, is a finite CP algebra of dimension 1, and then in particular actually it's just it does actually have QP bubbles. We should say this Taylor-Wiles method is usually used in the following way. You have some rho bar, some mod P representation, you have some lift of it, and you want to prove that the lift comes from an automorphic form, given that the mod P representation does. On the other hand, this method, somehow the potential here, means that you apply such an argument after replacing Q with some very large number field. And Cohen-Vanderberger had some great ideas about how you can kind of use that to still construct representations back over Q without knowing that they're actually modular. So it's some kind of nice thing. You can start with a mod P representation on kind of fairly great generality. We know that those so-called potential automorphic, and you can use that to produce lifts with given local properties. So if there are, for example, unramified lifts at places where P or these crystalline lifts for charity P, then you can produce global lifts. You don't actually know that the lift of Gauss sensation reconstruct actually comes from some automorphic form pi. But if you furthermore start with a mod P representation, it does start life knowing it's coming from modular forms, then you get as a bonus at the same time, you get automorphic forms out. So the kind of upshot of this kind of material is that for us, kind of to prove the theorem, I just need to construct the following thing. back again. Construct a representation of rho bar. The Calegari Q, the GLN and P bar for some time P, they're going to be the GLN P, which is absolutely irreducible. Irreducible if I put P bar. It's going to be unramified outside of P. I'm going to need the rho bar restricted to P combination group P admits this to admit the constraint admits zero, 1, up to n-1. If I just have those properties, I can actually construct the p-adic representation of these properties. I'm also going to want to know that rho bar itself is automorphic, so it comes from some. Okay, so I should say that these kind of machinery for doing these liftings and so on probably existed around 15 years ago.
Say the last one real far. Is it like anything that you don't need to know after I that comes to level 1?
I wouldn't need to know that, but I will in the application.
It's the weight.
It's the weight. It will come. What I will know for it comes from a different weight.
Okay.
Yeah. So maybe of some weighting level. Yeah. Right. Yeah. It will in the application in a minute come from level 1, obviously, and not obviously. So this kind of these conditions, you'll see the rest in a minute. We could have this could have been done maybe 15 years ago. It's kind of old. No one did it, but this part is actually quite new and it's working using its own a few years ago, much more recent. Okay, I hope you have about 2 minutes, but that should be just about enough time to tell you how to do this in our example. Because in some sense, the ingredients for making the construction now, and constructing the example, the thing that was possible with old since about 15 years ago is that you have these conditions, then some machine like this would make the Galois representation you want. What's even older is how to actually make something satisfying these conditions. And so this could have been done in the 80s, although it would have done. We're going to take P equals 107. F is the modular form the Eisenstein series E4 squared E6 times delta. So that's turns out to be an eigenform of weight. Eigenform weight 26 and level 1. So I'm not put together a bunch of level 1 things. And a calculation of no alkenes, again, that's sometime in the 1980s. He noted that there exists a weight, form G, weight 82, level 1. He was doing a computer search to try and find some examples of these. It wrote this paper that Brandon referred to yesterday about attainment criteria. They wanted examples. Such that the following thing happens. You take the mod 107 Galois representation for F, and which is something irreducible, and you twist it by the 6 atomic characters to the power 25. 25 here is 1 less than 26. You get the Galois representation G. So there's some congruence between these modular forms of different weights, at least after I do some twisting. And this fact here, and furthermore, it's kind of ironic. as usual, as a sort of normalized Q expansion, then 107 is not divide the eigenvalue of 107. That means that this is ordinary at the prime 107. These facts together, kind of easy exercise, I won't give the details. This implies that you can see what this mod P mod 107 representation looks like locally at 107. And it's isomorphic to the sum of two characters, and one of them is the minus 25th power of the mod P, the mod 107 sigmoid character, probably lambda 1 and lambda, sorry, direct sum, lambda 2, with lambda 1, lambda 2 unramified. So this is kind of the key properties that we want. I should just say, whenever you have this kind of ordinary condition, which is, let's say some eigenvalue is non-zero mod P, then you get some statement like this after semi-simplifying. So it's a little bit vague, but you could do the mod P representation of the whole thing is irreducible, mod 107 representation. When I restrict to a decomposition group, it could very well be reducible. There's no reason it should stay irreducible. And this statement here would then hold after you semi-simplify, but here it's holding on the nose, which is rare. And the fact that it's semi-simple is exactly corresponding to the existence of this other modular form. Okay, but now we've basically won. Sorry, I'm very slightly late, but I'm just going to do the punchline. So now we have a two-dimensional representation. That's kind of bad, because we know we can't solve this problem in dimension 2. But of course, there are lots of ways of taking a representation of some dimension and making representations of bigger dimension. And in particular, what we want to do is just take the, I guess, 105th symmetric power representation. I've got my numerology correct. So consider this representation. This has dimension 106, and now restrict it to the decomposition group, and then this is isomorphic to a kind of direct sum of characters, some kind of unramified characters times powers of sorry, times sort of I 25, I is 0 to who knows? Let's not worry. And now
it's 106.
And now a little exercise is to check that this is also isomorphic after commuting to some sum of sort of lambda j times the exercise using 25 and 6 at 55. So it's done the exercise for you. And now this is going from j from 0 to 105. And this thing does obviously have a lift of the same kind of way on time goes. The range, you just lift the unramified characters and you lift these and you win. The slightly more difficult exercise is to check that you can also get a 105-dimensional representation by very similar construction. That's a fun exercise.
You have to check it as a model.
I do have to say that I'm over time, so I'll stop and we can ask questions, and then you can ask your question. But yeah, let me answer Matt's question. Matt was like, how do you know this is automorphic? Like I had already said, Newton and Thorne, so I wouldn't write out history, but Newton and Thorne, this is an extremely useful theorem for us. They showed that for any modular form, modular eigenform of weight of, well, any weighted level, I guess, F, and any the symmetric powers of its Galois representations are automorphic to all N. Yeah, so pre-Newton and Thorne, you could have made all of this construction. So maybe in like 2010 or 11 or something, you could have run this argument and have to construct the Galois representations. And then everyone would have known that there were definitely going to be cuspidal forms, cuspidal forms of weight 1, weight 0, level 1, because everyone believes Lang's index that say they exist. And I should say, like, I mean, it was not universally known what the answer to this question was going to be, but we certainly would have had no way to prove that we actually had all these conditions. But because of this remarkable work of using Thorne, we now know the representations exist, so we actually get everything on the notes. Thank you.
So these are self-dual or essentially self-dual representation, and the lift.
Yes.
And
So-
therefore, they descend to some classical group.
Yes.
And if the dimension is odd, then it descends with its egomodular form, and so principle can determine whether by trace formula whether there are such.
Right. So what Michael's saying is that, quite correctly, is that I should point out that the GL2, of course, everything does have some symplectic structure, and so symmetric powers do have some self-duality as well, some orthogonal symplectic pairing. And the lifts we're going to construct certainly also, because the only way we know how to construct them is also they also have the same self-duality. And then the automorphic representations provably descend to symplectic or orthogonal groups as well. And so in principle could be detected by the trace form. I should say, of course, this gives you some construction of some cuspidal kind of cohomology classes for symplectic groups and so on, but that turns out to be much easier. It's much easier to be cuspidal or symplectic group than GLN. The problem is that the dimensions that we're working in are just too big. So like we're in dimension, like there is another example we can have, which is a bit more complicated, which is down to dimension 79. But Chenevier and Toby have developed a great kind of program of doing computations, and they can really compute the dimensions of all of these things at level 1 and any weight at all. But I think computationally get stuck in dimension around like about literally where the kind of the knowledge ran out, so around kind of dimension 27 or something.
But they don't get
right.
down
And exactly, and I think the problem is that it's not like it takes 10 times longer to run to go from 27 to 28 or something. It's even worse than that. I think it's still completely unclear whether you can ever do the computations in dimension like 32 or something, where you might really hope to find examples. What does come out of kind of the reason, like at least I believed before these things had to exist, is what you can do is because they have calculations in sort of all weights, not just weight 0. You can kind of ask what the sort of minimum weight is in which you see things at level 1. And as you get higher and higher, like the dimensions, you get closer and closer to having something. So kind of some kind of squinting at some charts suggests that there should be something in probably every dimension beyond about some number, it's about 30. But I don't know if we'll actually ever be able to compute it precisely. Yeah, I mean, there should be vast numbers of these things, and we're just constructing some tiny, I mean, we've constructed finitely many examples and very sparse, but yeah.
The other question is whether there is a hypersurface of this dimension is cohomology. Or a piece of this cohomology.
Yeah, so I think Michael's asking about like then making geometrically realizing these representations, which I haven't thought about. I mean, these are contributing to the cohomology of Schmidt varieties, I guess. But it's a bit scary because we're in level 1. But yeah, I have no idea. I think probably we don't know how to realize them as motives. Is that right? There must be some note about this in our paper. So whatever it says in our paper.
Well, I mean, it's going to be an example, but if you insist, it's probably going to insist that as well.
Yeah.
So I'm just curious about this isomorphic part of the representation.
Yes.
So the because G the 82. So if you so it's saying that the weight on the two sides doesn't match.
I mean,
you need the 81 on the right hand side and
Again, this sign convention for supersonic character is correct.
I mean, I'm hoping we can. If I add these numbers, I get 108, and So that's,
I mean, it's hungry.
I think it should be fine.
Okay.
But realistically, you don't want to see me try and check this in real time. Like, definitely no one else in the room wants to see that. So I should say, like, almost any question anyone's going to ask, the paper is very short and the introduction is very nice. And I think Frank also has a nice blog post about it. So maybe we should, yeah, defer questions. Ah, good. That is a good question. It's like, if you have, whenever you have this, it's called an example of companion forms, is do you then get examples? Well, we basically prove the answer is yes, provided that the image of the mod Q representation contains SL2 FP. Because I've kind of buried, I do want the symmetric power of these things to actually still be reducible. So if you have some kind of exceptional thing where the image is A4 or something, that's bad. But yeah, I mean, we have some general criteria, and you need the weight. You need like the weight -1 to be co-prime to P-1. So that calculation. But there's some short list of conditions, but we don't know that there are infinite many such. I mean, surely there are infinite many such things.
107 is the smallest.
But 107 is the smallest. Yeah, exactly. And we also do something. The other construction for 79 is similar, but it's what construction you make in the non-ordinary case. And then you work in dimension P. It turns out you can do this like 70 - 1. And with a bit more work, you can make that work. It's less obvious. And again, 79 is the smallest. I mean, 59 there's an example, but the image is too small. But 79, the image is probably something closely related to GL2 F79. Yeah, I think we should really stop for lunch. Sorry, Jason, you were going to say the same.